Now the next topic is that is modulus of complex number. What is meant by modulus? Modulus is always a positive quantity. So what about the modulus of a complex number? In real number, if we have -3, modulus of that is equal to 3. So modulus is always a standard that gives a positive value. So let z is equal to a plus iota b. Then modulus of z, that is denoted by into single lines, that is a sign of modulus, that is under root real part, that is square, plus square of imaginary part, that is b. Now by taking the square root of this sum, that is called modulus of a complex number. So modulus of z is always a greater than 0 quantity, that is a positive quantity. And it is always a real number. There is no involvement of negativity, and this is true for if all z belongs to real number, complex number. So we are here as same we done earlier, that is in the case of conjugate of complex number. We discussed so many properties of conjugate of a complex number. Now here we will discuss so many properties of modulus. So the next topic is that is properties of modulus. So the first one is mod z is equal to 0 if and only if z is equal to 0. Let z is equal to a plus iota b. Then we have mod z is equal to 0. That is under root, by the definition of modulus, under root a square plus b square is equal to 0. That implies a square plus b square is 0 under root if this is 0. This will happen if and only if a is 0 and b is 0, because if both of them are square quantity and both of them are always positive quantity, and sum of two positive quantity is never come out to be 0. So this should be happen only in the case when a is equal to 0 and b is equal to 0. This is possible if and only if z is equal to 0 plus iota 0, that is z is equal to 0. So the result is true. Mod z is equal to 0 if and only if z is equal to 0. Now the next property is, that is number 2. Mod z is always greater than equal to modulus of real part of z, and mod z is always greater than equal to imaginary part of modulus of imaginary part of z. So now we have to prove this. The proof is here. First we start with mod z. Mod z is under root a square plus b square if z is equal to a plus iota b. Now we can say mod z square is equal to, that is by taking the squaring on both sides we get this. It is obvious a square plus b square is greater than equal to a square, equal to when b is 0. So mod z square is greater than equal to a square. That implies mod z square is greater than equal to mod a square, because mod a is equal to under root a square. So mod a square is equal to a square. Now we get this if we see that we get on taking the square root on both sides, mod z is greater than equal to mod a. So what about a? A is the real part of z. So first result is proof mod z is greater than equal to modulus of real part of z. So the next one is we have to prove mod z is greater than equal to imaginary modulus of imaginary part of z. So we will do in the same manner as mod z is equal to under root a square plus b square. Now in the same manner mod z square is equal to a square plus b square. Now it is obvious sum of two square quantities greater than or equal to a single quantity square. This equal to is possible when a is 0, that is z is purely imaginary number. So in this case mod z square is greater than mod b square. As explained above, it can be b square is mod b whole square. That implies mod z is greater than equal to mod b. So what is b? B is the imaginary part of z. So mod z is greater than equal to modulus of imaginary part of z. So we have proved these two results. Now the third property is z into z bar is equal to mod z square. That is let z is equal to a plus eta b. That is we get z bar is equal to a minus eta b, and also we have mod z. So mod z is equal to under root a square plus b square. Now we will take first of all z into z bar. Now z into z bar is equal to a plus eta b into a minus eta b. That gives a plus b into a minus b, that is a square minus b square. That is a square minus eta square b square. That is a square plus b square. And a square plus b square is equal to mod z square, because mod z is equal to a plus eta b under root, and on squaring mod z square is mod z is a square plus b square, and mod z square is a square plus b square. Under root will be removed from this. So we get z into z bar is equal to mod z square. So that was our third property. That the product of complex number with this conjugate is equal to mod z square. So the next property is, that is number 4. That is mod z is equal to mod z bar. That is very simple property. Let z is equal to a plus eta b. Then z bar is equal to a minus eta b. So we have to find the modulus of these two quantities. So modulus of z is under root real part of z square, that is a square, plus square of imaginary part, that is b square. So mod z is under root a square plus b square. And what about mod of z bar? That is under root of real part square plus square of imaginary part. Here imaginary part is a plus eta minus b. That is a minus b whole square. Because generally we define the modulus of a plus eta b, that is plus sign in the complex numbers. So here imaginary part is minus b. This point should be noted by all the students. There will be no difference, but right manner is that is a square plus b square under root. So from these two observations we get mod z is equal to mod z bar. So we get our required result. Now the next property is, that is number 5. Mod z is equal to modulus of minus z. So that is a very simple part. Let z is equal to a plus eta b. Then what about its modulus? That is under root a square plus b square. So now we have to taking minus z, that is minus of a plus eta b. It becomes minus a minus eta b. So what about its modulus? That is under root minus a whole square plus minus b whole square. That gives a square plus b square. So from these two observations or result we get mod z is equal to modulus of minus z. So we get our result. That is very simple. So the next property is, we have to prove z1 over z2 is equal to z1 into z2 bar over modulus z2 square, where z2 complex number is not equal to 0. We have z1 over z2 which is equal to z1 over z2. Now multiplying and divide by conjugate of z2, that is z2 bar. So if we see that, we get z1 into z2 bar over z2 into z2 bar. As we know that z into z bar is equal to mod z square. Therefore we have z1 into z2 bar over mod z2 whole square. So with z2 is not equal to 0, that is already given. So we get z1 over z2 is equal to z1 into z2 bar over mod z2 whole square. So the next property is, that is property number 7, that is product of two complex numbers and after taking their modulus is equal to modulus of z1 into modulus of z2. Modulus of product of two complex number is equal to product of modulus of two complex number. So first of all we have to find here, as we know that mod z square is equal to z1 into z2 bar, that is z into z bar is equal to mod z square. Here we are considering z is equal to z1 into z2. So this is whole our complex number mod z square is equal to z into z bar. And also we know that Z1 bar into Z2 bar is equal to, that is Z1 into Z2 bar whole bar is equal to Z1 bar into Z2 bar. That is the properties of a conjugate number of a complex number. So the next one, we are going to take the product, that is Z1 into Z1 bar and Z2 into Z2 bar. Rearrange these terms. So as you familiar with that, Z into Z bar is equal to mod Z square. So we are using this property in these two terms, that is Z into Z bar is equal to mod Z square. So here we get Z1 into Z2 mod square is equal to Z1 square into mod Z2 square. So from here we get Z1 into Z2 whole modulus is equal to Z1 modulus into Z2 modulus. That was our required result. So the next one is, that is the 8 number property. Z1 over Z2 whole modulus is equal to Z1 modulus over Z2 modulus. So here proof is Z1 over Z2 mod square is equal to same Z into Z bar. Here we are taking Z is Z1 over Z2. So as we know that quotient property of conjugate number, it becomes Z1 bar over Z2 bar. This is the property of conjugate of complex number. Now taking Z1 into Z1 bar over Z2 into Z2 bar. As we know that Z into Z bar is equal to mod Z square. So it becomes mod Z1 square and it becomes mod Z2 square. So we get mod Z1 Z2 whole square is equal to modulus of Z1 square over modulus of Z2 square. That is, we get Z1 over Z2 modulus is equal to Z1 modulus over Z2 modulus. That was our required result. So that was the property of modulus of complex number. So the next property is discussed in next lecture, that is our mod Z1 plus Z2 whole square less than equal to mod Z1 plus Z2. Now the next property is, that is number 9 property, that states that modulus of Z1 plus Z2 is less than equal to modulus of Z1 plus modulus of Z2. Now proof is, that is modulus of Z1 plus Z2 whole square is equal to Z1 plus Z2 into Z1 bar plus Z2 bar. That is, if take this as Z, then Z into Z bar and whole modulus Z1 Z2 convert into Z1 bar plus Z2 bar by using the properties of addition of conjugate of complex number. So here the next one will be Z1 into Z1 bar plus Z1 into Z2 bar plus Z2 into Z1 bar plus Z2 into Z2 bar. Here we can see that Z into Z bar is equal to mod Z square. So we'll use this property in this step, that is mod Z1 square plus mod Z2 square. That is comes out from this. Also, if this is complex number, then what about its conjugate? Its conjugate is, that is conjugate on this and conjugate on this. That is, we can also write that mod Z1 square plus mod Z2 square plus Z1 into Z2 bar plus Z1 into Z2 bar whole bar, that gives mod Z1 square plus mod Z2 square plus, if we remember, Z plus Z bar is equal to over 2 is equal to real part of Z. So here if it is Z, then it is Z bar, then it is the 2 times real part of Z. So this is not complicated, just see it. And also we know that mod Z is greater than real part of Z. We also know that, so here we have real part of Z. So whole quantity of this is less than equal to mod Z square mod Z2 square plus 2 times mod Z1 Z2 bar, that is this. And that is mod Z1 into mod Z2 bar, that is equal to A square plus B square plus 2AB, that is mod Z1 plus mod Z2 whole square. So from the starting and end, we get that Z1 plus Z2 whole modulus square is less than equal to mod Z1 plus mod Z2 whole square. That gives Z1 plus Z2 modulus is less than equal to Z1 modulus plus Z2 modulus. So this was our property, and that will be used in the problems to solve such type of questions where we have to find maximum minimum value. So the next property is, that is the last property of modulus. These two properties are a little bit tough than the other properties, so see very carefully. The next property is mod Z1 minus Z2 is greater than equal to modulus of difference of modulus of two complex numbers. Modulus of difference of modulus of two complex numbers, that is modulus of Z1 minus Z2 is greater than equal to modulus of modulus Z1 minus modulus Z2, difference of modulus of two complex numbers. So we start with as Z1 can be written as Z1 minus Z2 plus Z2, that is a trick. So if we take mod Z1, which is always equal to mod Z1 minus Z2 plus Z2, and as we know that mod Z1 plus Z2 is less than equal to mod Z1 plus Z2 as done in the earlier property. So from the property 9, we have mod Z1 is less than equal to mod z1 minus z2 plus z2 by taking this is as a one complex number. So that implies mod z1 minus mod z2 less than equal to modulus of z1 minus z2. That is a number 1. Similarly, z2 is equal to z2 minus z1 plus z1 by taking this as one pair. So now taking the modulus of this, modulus of z2 is modulus of z2 minus z1 plus z1. So by using the property number 9, it is less than equal to mod z2 minus z1 plus modulus of z1. So again we get modulus of z2 minus modulus of z1 less than equal to modulus of z2 minus z1. That is modulus of z2 minus z1 is greater than equal to modulus of z2 minus z1. That is greater than equal to minus of modulus of z1 minus z2. That is number 2. So from 1 and 2, that is we get z2 minus z1 is greater than equal to maximum values of minus of mod z1 minus z2, comma modulus of z1 minus z2. As the same case, we know that mod A is equal to maximum value of minus A comma A. So here modulus of z2 minus z1 is greater than equal to modulus of mod z1 minus z2. Using this result, maximum of minus A and B is mod A. So here maximum of minus this and this is mod of this quantity. So this gave our result. So this is the main link that gives our result. So this was all about the modulus and its properties. So there is no confusion. That is mod A can be written as maximum. We get modulus of z2 minus z1 greater than equal to this quantity and modulus of z2 minus z1 is greater than equal to minus A. So we can say that these two quantities, this quantity is greater than these two quantities, it is maximum of these two quantities. So we can replace this maximum of these two quantities by modulus of A by definition of modulus of some real number. So do these two properties very carefully. These are very important properties of modulus.